Hello, today I'll be talking about hexahedral mesh repair via SOS relaxation. My name is Marschner, and I worked in this with David Palmer, Paul Zhang, and Justin Solomon. So our concerns hexahedral meshes, which have been shown to be beneficial over tetrahedral meshes for certain applications like finite element analysis. But one big problem with hex meshes is that most of the existing algorithms to create them often leave invalid hexes inside the mesh. And when we say invalid hex, we basically just mean a hex that's slightly turned inside out. And this is no longer suitable for finite element analysis. So ideally, we'd like to be able to identify which hexes in our mesh are invalid, and also to be able to take a mesh with invalid hexes and repair it so that there are no longer any invalid hexes. And this is what we set out to do in this work. So today I'll be talking about first how we can formalize the idea of quality of a hex, and then the mathematical background that we use to be able to solve the problem of finding the quality, and some implications of the method that we use. And eventually I'll get to how we can use this to actually repair meshes. So first we need to talk about how we actually mathematically represent the idea of the quality of a hex element. So if we look at this example hex, notice that when it's valid, it looks kind of just like a slightly deformed cube. But there's also this region where the faces of the hex intersect themselves, and when we consider this invalid. So when a hex is self-intersecting, it's invalid. And to be able to actually find the region where it's self-intersecting, we first need to talk about how we represent a hex. And so if you think about the 1D analog here, one way to represent a line segment is as a map, a linear map from the region from 0 to 1 onto this line segment. And similarly, we can define a hex element as a trilinear map from the unit cube onto the hex. And notice that the trilinear map has linear edges, a bilinear faces to the curved, and a trilinear interior. And so the linear map is quite simple to represent. We can just represent it with this function that takes as an input a point along the region 0 to 1, and as an output gives us the corresponding point on the line segment. And similarly, a trilinear map takes as an input a point in the unit cube, and as an output gives us the corresponding point in the actual hex element. And notice that the linear map just depends on v1 and v2, the endpoints of the line segment, and the trilinear map depends on the 8 vertices of the hex. And also, the linear map is just a polynomial here, and the trilinear map is also a polynomial. It's just a much more complicated one. So now that we have the trilinear map, we need a way to actually determine when it intersects itself. And so we can do this by computing the Jacobian determinant of the trilinear map. And this basically tells us a little bit about how the volume is changing at any point inside the hex. And so you can see here, I've plotted on this example hex, which is just the unit cube with the top rotated 180 degrees. And notice on the top and bottom planes, the volume isn't changing, so the Jacobian determinant is 1. But at the center, an entire plane of points is being taken to a single point. So the Jacobian determinant there is 0, and it's invalid. So to compute a single quality measure for the entire hex, we take the minimum over the entire reference domain of the Jacobian determinant of the map. And this gives us a measure of the quality of a hex. And so we want to be able to actually compute this quality. How can we do that? One way that's often used is to just compute it at the 8 vertices of a hex and then take the min of that. But as we've seen, this isn't always going to give the right answer. So for example, here, you can see that it misses the invalidity that occurs in the center of this hex. And so a better way to do this was proposed by Zhang et al. In 2017, and it uses this recursive like branch and bound procedure to find a bound on the minimum Jacobian. And we want to solve the same problem, but we take a different perspective by first looking at the underlying optimization problem that's at play here, and then applying results from optimization to this problem. And this allows us to compute some interesting facts about the hex quality problem. And so you can see this is the actual optimization problem that we're trying to solve. We just have a polynomial, the Jacobian determinant, and we're trying to find the greatest lower bound of this polynomial. And so we introduce this variable lambda, which we bound to always be less than the polynomial over the unit cube, and then we just maximize lambda, and so this gives us the greatest lower bound of the polynomial. All right, so now we have a way to represent hex quality as an optimization problem. But how do we actually solve this? Well, we can look at the types of optimization problems that are easy for us to solve. And one of the most basic is a linear program. A linear program has a feasible set that's a convex polytope. And the convexity of this set is one of the things that makes it so easy to solve. Slightly more complicated is a semi-definite program. Now we're optimizing over matrices, and we have constraints that these matrices are positive semi-definite. And this figure here illustrates the set of positive semi-definite matrices with a 1 along the diagonal, and notice it's a convex set. So positive semi-definite constraints are also convex constraints, which makes these types of problems also relatively easy. But if we look at the hex quality problem, we have this polynomial inequality constraint. And this is not convex, so it's not really that easy. And ideally, we'd be able to transform this constraint into something else, that's easier for us to solve. So let's think a little bit about what polynomial equality means. So if you look at this polynomial, you might wonder if it's positive over all of x, and it's kind of hard to tell this. But on the other hand, if you look at this polynomial, notice that it's in a special form, a sum of squares. And we know that this polynomial must be positive over all of x. And in fact, they're actually the same polynomial. One is just written in a form where we can easily tell whether it's positive. And this gives us the fact that if we can write a polynomial p of x as SOS, in the SOS form, then we know that it's positive over all x. And you might wonder, is the converse also true here? Well, it's true in certain cases. So it's one of the important ones is for all univariate polynomials. But in general, it's not true. And this leads to the idea that there's this gap between the set of polynomials that's SOS and the set of polynomials that's positive. All right, so if we have a given polynomial, we can prove that it's positive over all x if we can prove that you can write it as a sum of squares. And so we want to write a polynomial, say p of x, as the sum of, let's say, q's squared. And we can rewrite these q's as matrices with a matrix of coefficients and a matrix of the monomial basis, which we'll call x. And you can add along the sum, and you end up with this matrix capital Q, which just has all the coefficients of the Q functions in it. And notice we have Q transpose Q, which is a positive semi-definite matrix. So if you can write P of x as x transpose times A times x, where A is positive semi-definite, then we know that P of x is definitely an SOS polynomial, or can be written as an SOS polynomial. And so this gives us the fact that if that's like saying a polynomial is SOS is exactly the same as an SGP constraint. And so it's also a convex constraint. And so we can take a problem in this form where we have a polynomial inequality constraint, and we can transform it into an SOS constraint. And this is called SOS relaxation. Relaxation because, as I mentioned before, there's this gap between the set of SOS and the set of positive polynomials. But notice that we've taken a non-convex constraint that we can't easily solve, and we made it into a convex constraint that we can easily solve. And so it'd be really nice if we could apply this to our hex quality problem, because we have a polynomial inequality here. But notice in the hex quality problem, the polynomial inequality is only active over this compact domain, the unit cube, whereas we've been talking about SOS relaxation over an unbounded domain. And so we need to do a little bit more math before we can actually apply it to this problem. So we have this powerful tool of SOS relaxation, but we'd like to be able to apply it over compact domains, like the unit cube in the hex quality problem. So how can we represent a domain like this? Well, one way is with polynomials. So for example, the polynomials x and 1 minus x, if we consider the set where they're both positive, we end up with a range of x equals 0 to x equals 1. Another thing we might want to ask is whether a polynomial is positive over this way, like a domain like this. And so if you look at this polynomial, it's kind of hard to tell. But in contrast, if you look at this polynomial, notice that each of the terms here that's added or multiplied together is positive on its own over that domain. And so the entire polynomial must also be positive. And these are actually the exact same polynomial. One of them is just in a different form. And so this special form, in this special form, we have the f's, which are the polynomials that define the domain, multiplied by just sum of squares polynomials, which are represented by s here. And so we know that if we can write a polynomial in this form, then it's definitely positive over the set defined, over the set of where the f's are positive. And we might wonder whether the converse of this is also true. And so in his positive Stellensatz, Marschner said that yes, for certain domains this is true, but only if you take the degrees of the s polynomials arbitrarily high. And so our hex problem does satisfy the assumptions of Marschner's positive Stellensatz, so we can apply it here. And we can rewrite our compact domain as these 6 different polynomials. Notice they're just like x and 1 minus x essentially. And with those f polynomials, we can rewrite the polynomial that we were constrained to be positive, which is the Jacobian determinant minus lambda, in this Marschner form of the s's plus, or s0 plus s1 times f1 and so on. And so then notice that we have 7 SOS polynomials, and we can constrain each of these to be SOS. So we have this constraint on S0, and then 6 other SOS constraints. And so now notice that we've transformed our original polynomial inequality constraint over a compact domain into 7 SOS constraints. And so now our problem is convex, and it's now easy to solve. And we can actually implement it quite easily also, for example, in the SOS toolbox in YALMIP. And so you can see here that it's actually not even that many lines of code. And one thing to note is that we have to pass the degree of the SOS polynomials. And if you remember when I was talking about Putner's positive Stellensatz, I mentioned that we had to take the degree of these polynomials arbitrarily high. We can't actually do this in practice. So we just want to choose a degree that's high enough so that the gap between the polynomials in Putner's form and the polynomials that are positive on this set is numerically 0. And we call this exact recovery. Okay, and we might want to ask whether we've actually achieved exact recovery in our case. And so we chose to take, or we found that degree 4 does lead exact recovery. And one way we can determine that we've achieved exact recovery is by graphing the difference between the true Jacobian, or the true minimum Jacobian determinant evaluated just with sampling, and the minimum Jacobian determinant calculated with our SOS method. And you can notice here that it's numerically 0. And so we say that we have achieved exact recovery with a degree equals 4. All right, and then we can now use this to check the invalidity of lots of different meshes. And so notice here, I plotted in red the invalid hex elements of all these, or in these 3 different meshes. So now we have a way to find the minimum Jacobian determinant of a hex. But we'd like to also be able to find the location in the hex at which this minimum occurs. And this ends up being quite a natural extension from the SOS problem we just talked about. But to understand this extension, we first have to go back and look at the underlying optimization problem here. And so if we were trying to find the minimum of a polynomial, intuitively, we can kind of just point at it. And this maybe corresponds to this intuitive way to write an optimization problem of just finding the argument of p of x with respect to x. But this isn't really an optimization problem that we can easily solve. And so maybe a different way to think about it is if we imagine that our polynomial is a potential and we're placing masses along it, in such a way that we want to achieve the lowest energy possible. And so clearly, the way we place these masses to achieve the lowest energy is to place them all at the minimum value of the potential polynomial. And so we can kind of formalize this idea with measures. And so we have this optimization problem where we're searching for a measure such that when we integrate a polynomial p of x against this measure, we get the minimum. And we also have this constraint that the measure is a valid probability measure on the set S, or the set that we're optimizing over, or the set that the polynomial, or that we're integrating the polynomial over. And so just as when we were placing the masses, the optimal way to place them was all at the minimum of the polynomial. The optimal value of this measure is clearly just going to be a delta function supported at only x star, the minimum value of the polynomial. So this is a nice problem that lets us find the value at which a minimum of a polynomial occurs. However, in the way it's currently described as a minimization over measures, it's not something that we can easily solve. So we'd like to be able to rewrite this problem in such a way that we can actually solve it. So one way we can think of measures in a different way is as moments instead. And so, for example, the center of mass is the first moment of a mass distribution, and we get this by integrating x with respect to the mass distribution. And similarly, we have the second moment, which is the moment of inertia. And so since we're just integrating our moment or our measure since we're always integrating a polynomial p of x with respect to our measure, we can rewrite this as the sum of integrals of monomials with respect to the measure. And notice that these are just the moments. So we can rewrite the integral of a polynomial with respect to this measure as the weighted average where the weights are the coefficients of the polynomial of the moments of this measure. All right, and so this allows us to rewrite this optimization problem. Instead of optimizing over measure, like the infinite set of measures now, we're just optimizing over this vector of moments. And so we also have to rewrite the constraint that the measure is a valid probability constraint on the set S. And so we can do this with these 3 constraints, which kind of look complicated, but in fact, the first 2 are just constraining the measure to be positive on the set S. And the last one is just constraining the 0th moment to be 0. And this is the moment relaxation developed by Lasserre. Developed by Lasserre for multivariate polynomials, And so to actually implement this, we have to have a way to represent moments. And we can do this with a moment matrix, which is basically just a Hankel matrix of all the moments up to some value or to some degree. And so here it's up to 2m. And so in practice, here are some examples of moment matrices. So on the left is the moment matrix of a delta function. And so notice that the matrix is rank 1, and since the delta is supported at 2, the first moment here has a value of 2. And similarly, on the right is an example of the moment matrix for a Gaussian. And notice that the mean here is 0, and the standard deviation is 1, and we can recover those as the first and second moments of the moment matrix. All right, so if we write the constraints in this moment relaxation in terms of moment matrices, notice now that these are just constraints on matrices being positive semi-definite. And so this is an SGP problem. And you might actually notice that this problem looks quite similar to our SOS relaxation. And in fact, these are duals of each other. And this means that it's actually really easy to formulate the moment relaxation since we've already formulated the SOS relaxation. So we can write that and implement it. And then here you can notice we have the hex from the beginning, or example hex from the beginning. And now I've plotted the argument as this red dot. And notice how it kind of follows the point in the hex that looks to be intuitively the most like turned inside out. All right, and another cool thing that the moment relaxation allows us to do is, so we've found this moment matrix, and we expect it to be the moment matrix that corresponds with delta. So we expect it to be rank 1. And so if we look at the second eigenvalue, we would expect this to be 0. And so this is another way we can evaluate how good our relaxation is by plotting how close the second eigenvalue is to 0. And here you can see that essentially the second eigenvalue is 0. And so this is another reason why we say that the degree of 4 that we chose for our SOS relaxation is sufficient. At the beginning of this talk, I mentioned that it would be useful to be able to create an algorithm to repair meshes with invalid hexes. Now that we have the ability to find the argmin of the Jacobian determinant, we can use this to find such an algorithm. So a good first step would be to find an algorithm to repair a single hex element. And so we can do this with this optimization problem here, where we have V0 is the initial positions of the vertices, and we're trying to find a new position of these vertices such that we minimize the distance between this new position and the initial position, and so that the Jacobian determinant is positive everywhere in the hex. And notice here that the Jacobian determinant depends on the vertices V. All right, but this constraint is very difficult to enforce in practice. So we can simplify it to a constraint like this, where instead of optimizing over the entire hex, we pick one single point and find a set of vertices such that the Jacobian determinant is positive at that point. And so one such point that we already know how to find is the argmin. So we can rewrite this problem in a simpler way as finding the minimal distance we can move the vertices such that the hex is still is valid at the point at which it was previously the most invalid. And so you might notice that this doesn't actually guarantee that the hex will be valid everywhere, but we'll hope that it gets us closer. And then we can find the argument of the new hex we have and continue this process until we end up with a hex that's no longer invalid. And so this gives us an algorithm to repair a single hex element, and we call it pi. And we can see the algorithm working here. And so we're starting with this hex you can see is very invalid. Notice that the faces are kind of intersecting themselves. And then if we apply the algorithm, all right, so we've ended up with this hex. Maybe it still looks a little weird, but the Jacobian determinant is positive everywhere, and you can notice that the faces are no longer intersecting themselves. All right, and now we can build off this hex element repair algorithm to build an algorithm that can repair an entire mesh. And so a good first step to doing this would be to just apply the element repair algorithm to each element in the hex. And so we do this, but when we did this, we didn't care about the fact that that hex elements in a mesh have to have certain vertices that they share with their neighbors. So since we didn't care about this, we no longer have a hex or a mesh that's actually valid. We just have a collection of hexes. And so we need to do something like we've done with the quads here, so that we take these disjoint hexes and make them into a mesh. And we can do this by taking a weighted average. So for each vertex, we take an average of the position it was initially in and the position it is in all of the hexes that share that vertex. And so when we take this average, we might take some of the hexes that we previously fixed and make them invalid again. So we have to continue this procedure. We can do it iteratively until we no longer have any invalid hexes. And at this point, our hex will be fixed, and you can see it's working here with the bunny. So the yellow or the blue is the number of invalid hexes, and notice that it goes down. And when we get to iteration 19, there's no longer any invalid hexes in the bunny, so the bunny is fixed. And we can also apply this to all of these meshes. So here, the red represents how far each edge moved. And notice that the red is generally quite localized, and this is because we only really need to move just a few hexes around the hexes that are invalid. Okay, so I've defined the quality of a hex and talked about how we can use SOS relaxation to find this quality in a way that allows us to calculate interesting things like the argument, which we can eventually use to create an algorithm for repairing meshes. Lastly, I'd just like to talk about why SOS relaxation is so cool. So I'm sure all of you see lots of polynomials in your everyday life, and every time you run into a polynomial you need to optimize, especially a low degree one, SOS relaxation can be really useful for doing that. So I've been looking at a couple areas in geometry where SOS relaxation ends up being really important. And I'd love to hear from you if you run into any problems that you think can be solved with SOS relaxation. So the code for everything that I talked about here today will be available on my GitHub in this repository. And if you have any questions, feel free to email me. Thank you very much for listening.